Hello again. These are the notes for Unit 4, Day 6, and we're continuing our discussion on related rates problems. And now we're hitting the advanced ones. And we're still working with this essential question: how will I decode calculus problems? So again, we're reading strategically. I know I didn't mention that in the last video, but we're doing some strategic reading, maybe some avid techniques on circling and underlining information, and then we're following those steps for the solution process. Okay, so looking at example 5 here. It says the radius of a sphere is increasing at a constant rate of 0.04 centimeters per second. So we got some units here. Note the volume of a sphere with radius r is v equals 4/3 pi r cubed. So notice this is an old AP question. They give you the volume equation right there. They do that a lot in free response questions. At the time when the volume and the radius of the sphere are increasing at the same numerical rate. Okay, what is the radius? So a couple of things to to highlight is it's a volume question, or maybe just circle that equation. There's the question: what is the radius? So when we look at this, right, it's kind of like this. It's kind of like we're blowing up a balloon, right? And as the air the volume increases, right? And we're increasing that, maybe 0.5 millimeters a second. And so that's the kind of the scenario that we're looking at. So since I run this video to the end, that thing's going to end up popping. I'll keep you in suspense. Okay, so our radius is, leave it right there. There we go, increase radius. So we have this information here. Our rate is 0.04 centimeters per second. Okay, so we know that's r prime. It's a rate. It tells us it's a rate. Even if it didn't tell us it's a rate, the unit centimeters per second would be an indicator that that's a derivative. That's a rate of change. Okay, what else do we have here? That's really the only numerical information we have, but we do have this information. The volume and the radius are increasing at the same numerical rate. Okay, so what that means is that v prime is equal to r prime. Okay, and that's the still shot. It says at some time t, this is happening. So that's kind of like our still shot. So here is our model, our sketch, so to speak. We have a sphere, we've got a radius that's measured from the center to the edge. And what we want to know is, what is the radius? That's what we want to find. Okay, so they gave us the equation. V is 4/3 pi r cubed. We've differentiated this already. So we know that I'm using the Leibniz notation here just to mix it up a little bit for you, just so that you get used to seeing these different notations. dv dt equals 4/3 pi times 3 pi r squared, right? We got a power on here, so we're doing a power rule, times dr dt, right? So I know these, again, this is the Leibniz notation. So putting that in prime notation looks like that. What I did is I simplified this, right? We talked about canceling the 3's a little earlier, or in the last video. Yeah, the last video. Okay, so my snapshot really isn't going to help me here. I don't have a radius, so I can't calculate a volume, or vice versa. So that's not going to help us out anyway. But we do know that v prime and r prime are the same, so we can literally divide these out. So what that means is that if we divide it out, if I replaced v with r prime, then we'd have, divided by r prime, we'd have 1 over here on the left. So we have 1 equals 4 pi r squared. And notice this is all no calculator, right? We're just going to bring the 4 pi, we're just going to pi along. We're going to divide by the 4 pi, and then we're going to square root it. So our radius is 1 over 4 pi, and then square rooting that. It's a pretty tiny radius, come to think of it. Notice the numeric value of 0.04 centimeters per second doesn't really come into play here, right? Because of that the special situation of the volume and the radius increasing at the same rate. So just a caveat here before I move on. Oh, I'll throw on the centimeters, right? They gave us units. Sorry about that. They gave us units, so we should have units in our answer. A little caveat here, a little extension of this problem. This criteria here, volume and the radius of the sphere increasing at the same numerical rate, they could mix this up. They could say, hey, the volume is increasing at twice the rate of increase of the radius. You know, where now v prime would be 2r prime. So they could kind of mess with that that relationship and then introduce another value out here where now this would be 3r prime and we'd have a 3 out here or a 2 or something like that. So those are kind of ways we could modify this question a little bit just to make another, no pun intended, another related question, but with a different numeric answer. Okay, this is a really common question. So we've got a street light here, we've got a person walking, and of course the street light's going to cast a shadow on that person. And so it says a person whose height is 6 feet is walking away from the base of a street light along a straight path at a rate of 4 feet per second. If the height of the street light is 15 feet, what is the rate at which a person's shadow is lengthening? So the farther the way this person gets, the longer its shadow gets. And so what we're doing here is we're looking at similar triangles. And we'll get to that in a second. It is a calculator question, and we know this just by even looking at the options for answers, since they're in decimals. Then we know that we're definitely dealing with a calculator problem. So the rate at which a person's shadow is lengthening. So rate at which it would be a derivative, right? I'm going to call the person's shadow, I'm going to call that S. So this is S prime. Okay, so I'm going to call that S. We know the person has a height of 6, so I'm starting to get a sketch here, or at least annotate the sketch I have. The rate of the person walking, where am I? Straight line path. The rate the person's walking is 4 feet per second, and so they're walking away from the base of the street light. So that is this distance right here between the person and the street light, and so that is increasing at a rate of 4 feet per second. So that is x prime, if that makes sense. So let me kind of clarify that. This person is standing at a street light and they're walking away. And so x is getting bigger because they're walking away from the street light. And it's getting bigger at a rate of 4 feet per second. And so that's a lot of people kind of feel like 4 should be the answer to the question. Obviously it's not, because it's not even one of the options. But so you have to kind of really look at this as, okay, x is increasing at 4 feet per second. We could change this problem up by having the person walk towards the street light at that rate, and so x would be getting smaller, and then the rate would be negative 4 feet per second. So we could change up the problem like that. Okay, so here's the similar triangles. We have a little triangle here, height of 6, length of s, and hypotenuse here. And then we have a big triangle, height of 15, length of x plus s, and then the hypotenuse here. So the similar triangles then means I can just match up corresponding sides, if you remember that. So 6 over s, so here's that tiny triangle, right? It's the height over the shadow length, equals the big triangle, 15 over x plus s. And so we can differentiate this to get our related rates expression. Before I do that, though, because that seems like something really difficult to differentiate, I'm actually going to manipulate this first. So I'm going to cross multiply. And then I'm going to distribute the 6. And then I'm going to take the 6s and subtract it to bring it over to here. So I have 9s equals 6x, and then I'm going to divide by 9. Oh, I guess I'm going to differentiate. I guess, oh, that makes even more sense, actually. Let me reverse that. Why divide when I can just differentiate and get a related rate right away? So before I do that, though, notice I took it from a equivalent ratio, because that's what we do with similar triangles. And I manipulated the variables algebraically until I got something much more simple to differentiate. So differentiating this is 9 times s prime and equals 6 times x prime. And so now I can go ahead and put in my x prime, which is 4. I don't need a still shot because I don't have any s's and I don't have any x's, right? I've differentiated them all and they were all to the first power. So those all go away with the differentiation process. And so I have 6 times 4 over 9, and that's 24 over 9, which I could reduce, but I'm not worried about that. And I bet we have units. Yeah, it looks like, okay, we have a derivative, so it's going to be a per, right? It's going to be a rate, and I see feet, and I see seconds, so it's got to be a foot per second. Oh, it's multiple choice. I shouldn't have had to think about that much. So looking at so how do I pick 24/9 out of this lineup? Well, we know 9 goes into 24 2 times, and then it's bigger than 2 times, but 9 does not go into 24 3 times, so we know it can't be C. We know it can't be A. B is the only one that's 2 point something, so it's got to be B. Okay, let's look at the third one. We're going to do some trig in here now. I'll get the triangle shown above. And if theta increases at a constant rate of 3 radians per minute, at what rate is x increasing? So looking at this, this is 5, which means it's constant. So if theta is increasing, that means the hypotenuse here is kind of rotating outward, making that angle bigger. But if the hypotenuse rotates outward, then x has got to be getting longer. Okay. And if x is getting longer, then, and this is staying at 5, then this base must be changing as well. It's just that it's not entering into the solution of the problem. So we really need to, it says, theta increases at a constant rate of 3 radians per minute. At what rate is x increasing in units per minute when x equals 3 units? So we're going to relate, anytime we can relate it to a constant, that's advantageous. So we're going to relate these 3 variables. So I see it's a right triangle. I see I have an opposite and a hypotenuse. Okay, so I'm looking at a SOHCAHTOA relationship. And let's take a look at what the question is. What rate is x increasing? So that's our x prime, right? It's a rate. Okay, and we know that our angle is increasing at another rate of 3 radians per minute, excuse me. So that's our theta prime. We know x is equal to 3. And we know that opposite and the hypotenuse is the sine relationship. So opposite is x, hypotenuse is 5. And I am actually going to get rid of that. I don't want to do a quotient rule. I'm going to get rid of that fraction. Kind of like the same thing was true with the other one, right? We had a fraction equal to a fraction. That would have been a lot of quotient rule. Okay, so I'm going to differentiate that. Do I need a still shot? Let's take a look at that. Okay, so 5 sine theta, derivative is 5 cosine theta times theta prime. And then the derivative of x is 1 x prime. So there's my related rate expression. And it looks like I need a cosine, huh? So I'm going to need a still shot. So my still shot is looking at the fact that this is 3 and this is 5. What does this have to be in order for that to be a right triangle? So my still shot involves Pythagorean's theorem. And so my unlabeled side in this instant has to be 4, right? 3, 4, 5 triangle. And that helps me with the cosine, because the cosine of theta is adjacent over hypotenuse, right? So it's 4/5. So this is kind of cool because I don't really have to deal with any trig per se, unit circle stuff, or can't do any calculator stuff. I can just take this ratio 4/5 and substitute it right in for this whole trigonometric function. Because, SOHCAHTOA tells me that cosine and sine and tangent are all just ratios, they're all just fractions. So I have 5 times 4/5 times theta prime, which is 3 from the problem, equals x prime. And so that's going to be my answer. So it looks like my 5's cancel, and I get 4 times 3, which is 12. So the answer here would be E. Okay, let's take a look at example 8 here. The radius of a circle is increasing at a constant rate of 2 meters per second. What is the rate of increase in the area of the circle at the instance when the circumference is 20 pi meters? So this is relating not just area, but area and circumference. Okay, so we've dealt with both area and circumference already. You might want to try to pause the video and see if you can kind of combine the two things. There's lots of ways to do this, and give it a shot, see what you can come up with, and then start the video up again, and I'll show you one possible way to do this. Okay, if you're tuning back in, I'm assuming you've tried it and have an answer that you think would be the correct answer. Okay, so like I said, we're combining area and circumference. We have a radius increasing at 0.2 meters per second, so that's r prime. And then we have, says what is the rate of increase of the area of the circle at the instance when circumference is 20 pi meters? So we know C is 20 pi, and we want to find A prime. So we need to relate A prime and C, which we don't have an equation for. But we know A is pi r squared, and we know circumference is 2 pi r. And so if I differentiate A prime, because it's asking me to find A prime, right? So I'm going to differentiate A prime, and that's going to be pi times 2r r prime, right? That's a derivative, related derivative for r squared. And my still shot is going to be the fact that I am at 20 pi meters for circumference. And so that gives me a radius of so 20 pi equals 2 pi r. I'm going to divide out the 2 pi. That gives me a radius of 10. And so I get pi times 2 times 10 times r prime. So my still shot is where I used my circumference. I had to differentiate A prime because that's what it was asking for. So, so for my still shot, I got my circumference. I was able to put that into the related rates expression, and then multiplying this all out, let's see, 10 times 0.2 is 2. So it looks like I have 4 pi for my related rate, my rate of change of area. Said that wrong. Okay, so that must be, looking at the answers, must be answer C. Okay. So this is only one possible way to work this problem. Like I said, there's other ways where we can combine A as a function of C and differentiate that. There's a lot of options there, and we can discuss those options when we get in the classroom after we do the takeaways, if you'd like to.